where Charles Rezk is going to talk about calculations in multiplicative stable homotopy theory at height 2.
Hi, thank you. Well, that title, I guess, describes this talk. I really want to give kind of a broad overview, and then I'll sort of give an example of a calculation that is easy to do and interesting. There won't be much reimagining in this talk. I apologize for that. Someone wrote this announcement on the board. I don't know. All right, so let me remind you, formal group. I mean, I don't have to say what a formal group is at this point, right? So I'll talk about a formal group over A. I'll just remind you, just in case, that formal group is a kind of coordinate-free version of a formal group law. So it's got a function sheaf, function ring, which is isomorphic in some way to a power series ring. You know, it's a coalgebra. And so this is how you get the formal group law from a formal group, by picking a coordinate on it. Okay. So the key thing I need to tell you is what an isogeny of formal groups is. A formal group, well, it's some kind of Hopf algebra. So there's a notion of commutative Hopf algebra, so there's some notion of a homomorphism. An isogeny is a particular kind of homomorphism. Like that, F, such that if you take the resulting map on function rings, which goes in the other direction, F upper star, there should be finite and locally free. The nice thing about that is when that happens, you have a very nice notion of a kernel. You can do this even more generally, but they're nice if you have an isogeny. So the kernel of F is built by taking the obvious ring of functions, OK, where I tensor down along this map from OG prime to OG down to the ground ring. But the observation is that if you have an isogeny, then this gadget is finite and locally free over A. So it's a finite group scheme over A. Commutative group scheme for A. There's a notion of degree, which is basically the rank of this map, or if you like, the rank of this OK as a module over A. So there's the degree of F. That's just the rank. OK over A. It's really only defined locally somehow, but very soon A will be a local ring, so that won't matter. So here's a non-example. So let's take the simplest example of a homomorphism we can think of. I'll take the multiplicative group. That's defined, formal multiplicative groups defined over Z. And let's take the P series. This is all over Z. So in a coordinate, you know what this is. You pull back your coordinate. It's something like px plus blah, blah, blah plus x to the p. Well, that's not an isogeny. However, if you go somewhere nearby, it becomes an isogeny. So if I go to the rational setting, this actually becomes an isomorphism rationally. Meaning if I look over the base ring Q, any isomorphism in an isogeny. So this is an isogeny of degree 1 in that case. And on the other hand, I could go to mod P, or I could even look over the p-adics. In that case, it's an isogeny. It's an isogeny of degree P. All right. So one thing you learn here is if you want this nice notion of kernel, you have to go to a place where your homomorphisms are isogeny. Since you particularly like the P series, you want to live in a place where the P series is itself an isogeny. That limits the sort of phenomena that you might want to look at here. I'm going to erase this now. Let's see. Here's an example I'll need to talk about. This is the Frobenius isogeny. So if I have a ring of characteristic P, and my group lives over it, formal group, there's always a Frobenius isogeny of P to the rth power. So I'll call it F to the R. It goes from G to a base change of G along phi to the R. Phi is the endomorphism of A given by the pth power map. So I can pull back my group along that homomorphism. And the Frobenius isogeny is also given by that formula. It's given by the relative Frobenius on formal schemes. So that's a canonically defined isogeny that you have whenever you're in characteristic P. I'm writing very large on these boards today. Over a field K of characteristic P, things are even better. Whenever you have an isogeny, let's say this is degree P to the R, all isogenies have prime power, P power degree for the reason that you'll see. They always factor canonically through Frobenius. So I have the Frobenius isogeny, F to the R, and there exists a unique factorization through an isomorphism. So over a field, basically the only isogenies, all isogenies are built from Frobenius and isomorphisms. All right. So what I want to do is I want to fit this into a kind of structure, and I need to therefore tell you about deformations. So I'm headed towards thinking about Morava E theory. So that's a commutative S algebra. I'm interested in power operations for that ring. Morava E theory is associated to deformations of formal groups. So let me tell you how this works. I'm going to fix a single formal group, distinguished, called G0. This will live over K. So K is supposed to be a perfect field, characteristic P. G0 is going to have the property that its P series is an isogeny of degree P to the N. So it's a height n formal group. So I'm going to define the notion of a deformation structure relative to this fixed guy. So let's give an arbitrary formal group over A. A is going to be a complete local ring. And I'll define a set. Let's call this script D of GA. What's this supposed to be? This will be the set of pairs. I'll have an I and an alpha. I is an inclusion of the field K, that K, into A mod its maximal ideal. And then alpha is an isomorphism of formal groups from the base change of G0 to A mod M to the base change of G to A mod M. Let's write it like that. Okay. So if I have a deformation structure on my GA, I say it's a deformation of G0. But I'm going to think of the deformation structure as something a little bit separate. It's a piece of structure you add to the formal group. Here's a remark. I can push forward deformations along isogenies. So if I have an isogeny of such, let's say, G to G prime, this is defined over A, then I have a corresponding map, it's called F lower star, from the set of deformation structures on G to the set of deformation structures on G prime. Well, why is that? Oh, the reason's still up there. It's because of that unique factorization property. Let me write that out. Let's see. Oops, why did I do that? So, well, there's nothing really to say. Right? I have an isogeny, but But then it's a deformation. G is a deformation, or equipped with a deformation structure. So there's an isomorphism alpha from G0 to G at the special fiber, which is A mod M. Well, F, the isogeny, has sort of a base change of the special fiber. Call that F G mod M. And well, the observation is there exists a unique factorization through Frobenius. So phi to the r star I star G0, this is F to the r, and then there's a unique alpha prime. So the formula is F star of I alpha. It's something like, I composed with phi to the r alpha prime. All right. So you can push forward isogenies. Sorry, you can push forward deformations. Here's an exercise that you can do to make sure that you understood the definitions, I guess. So again, if I have Fp is an A, well, there are two different ways I can move a deformation from G to the base change of dG along the Beath power map. One thing I can do is I can push forward along Frobenius. Did I give this a name? Yep, F lower star. F now, capital F is Frobenius. The other thing I can do is I can base change. I can always pull back a deformation structure along a ring homomorphism. So I'll pull back along phi. So this is the phi from A to A that I wrote down before, Beath power map. And the exercise is that these are actually the same. It's supposed to be a tautology. So it's supposed to be an easy exercise. But I won't do it. All right. So I've set up some stuff related to deformations. What's going to happen? Now I'm going to take all these deformations and put them in a pile. This is the pile of deformation structures. So if I have a complete local ring,